In today's video, here is a nice problem regarding arithmetical number theory. Here is the following statement. Find all n as integer numbers. Satisfy this following statement. We have n is multiplied by 2 to the n minus number 1 plus number 4 is a perfect square. Okay? So our goal, we are going to find the appropriate values of n in order to have this set up as a perfect square. Okay? So let's go through the solution to see how to deal with this one. Okay? We are saying this term is a perfect square, which means it's going to be written on this form. N is multiplied by 2 to the n minus number 1 plus number 4 equals x squared as a perfect square. Okay? So before doing anything here, so let's put n, if we have n, strictly superior than number 1. Because n equals 1 is not going to give us a perfect square. And also n equals 1 is not going to give us a power of 2. This power of 2 is going to be disappear if n equals 1. Since we have number 4 here, we have x squared here. By moving this number 4 to the right, I will create a difference of two squares. Then we will factor out that. Okay? So let's do that. So we'll have n is multiplied by 2 to the n minus number 1 equals x minus 2 factor x plus 2. Okay? It's very simple. It's very clear statement here. Since the left hand side of this equation is even, which means the right hand side of this equation must be even as well. So since x minus 2 and x plus number 2 have the same parity, which means both of them are even. This is even. This one also is even. So working on this one like this is not going to help us at all. Okay? So let's set x minus 2 equals 2 is multiplied by m. Okay, let's add number 4 on both sides. If I'm going to do that, I will get x plus 2 equals 2m plus number 4. Okay, so by forming this product and replace its value here, so I get here n is multiplied by 2 to the n minus number 1 equals 2m factor 2m plus number 4. So I'm going to take number 2 out of this one and number 2 out of this one to make number 4 as a multiplier. So I will have here 4 is multiplied by m factor m plus number 2. Then divide both sides by number 4. I get n is multiplied by 2 to the n minus 3 equals m factor m plus number 2. So if you take a look carefully at this product, both terms of this product are even because the left hand side of this equation is even. In addition, both of them have the same parity because you have m, okay, as an even. You add a number 2 on it, you will get the same parity, which means this one is an even. This one also is an even. This one also is not going to help us at all because working on both terms as an even product is not going to give us any information about the left hand side of this equation. Okay? If it is going to give us any information, which means both of them are going to share number 2 as a power. But we don't know how much is going to go to here, how much is going to go to this one. Okay? And then also we don't know anything about n. Okay, so how to fix this issue and create a nice expression where we can have a clear image to solve this equation. Okay, so let's do the second substitution. Since we know both of the terms are even as we did previously, so let's set also m equals 2c. Okay, if I'm going to do that, let's add number 2 on both sides. I get m plus 2 equals 2c plus number 2. Okay, let's do the same thing by replacing these two terms into this product. I get the following. I get n is multiplied by 2 to the n minus 3 equals 2c factor 2c plus number 2. Let's take number 2 out of this one, take number 2 out of this one, and make number 4 as a common factor. So I will get here 4 is multiplied by c is multiplied by c plus number 1. Okay, then divide both sides by number 4. I get n is multiplied by 2 to the n minus 5, because this one 4 is the same as 2 squared. So we are going to decrease this exponent by number 2 because we are dividing by 2 squared. So equals c is multiplied by c plus number 1. Okay, so I have ended with very nice expression here. Let's take this equation at the top and continue work on it. Now here is a nice and important thing. Since we know this product is a even, because the left hand side of this equation is a even. Okay, this is nice. In addition, another good thing here, now we have transferred our expression which was even into the product involving the odd and even integer. So since c and c plus number 1 have the opposite parity, which means the even term of this product is going to absorb the whole power of 2. Okay, but the other one, which is odd, is going to take nothing from the power of 2, which means it's going to give us a nice and clear image how to solve this equation. Okay, now let's break this one into 2 cases, but we don't know which one is a even, which one is a odd. Let's assume c plus number 1 is a even, the other one is odd. I'm going to do this case. I let you guys do another case, because this video I wanted to make this very long. I'm going to start with a challenged one. Okay, so let's assume case number 1, if c plus number 1 is a even, which means c is a odd. Okay, or 1 is a even, which means it's going to write on this form: c plus number 1 equals 2 to the n minus 5 is multiplied by a. Okay, what is a? A is the same natural number. Okay, and c also is a natural number, and then also I get c, which means c equals b, where n equals a is multiplied by b. Let's go through with that. So we know this term is a even, is going to take this form, because if you are going to ignore this a, leave it as a power of 2, since this one is a even, immediately this one have an odd factor, it will have a problem. Okay, so we should put it on this form. If a is equals 1, that's fine, the whole thing goes towards number 2. Okay, so b must be odd. Why b is odd? Because c is odd. Okay, we might say why n equals a is multiplied by b, because n was a component of 2 integers. We may have a product into this one. Okay, so but we don't care about a is odd or even. If he's even, is going towards this number 2, we still have an even. If a is odd, we still have an even, because even is multiplied by odd, is still always will have even. Okay, so we don't care about what's the parity of a. Okay, but now we are going to fall in problem. Here is a nice observation here. We know 2 to the n minus 5 is strictly superior than n, but which condition this one makes this one is bigger than this one? When we have n is strictly superior than 8. But we are not going to keep plugging the values of n in order to say this one is strictly superior than this one, in order to say this one is bigger than this one. We are going to prove this one by induction hypothesis. Okay, so for n equals 9, we know 2 to the 9 minus 5, which equals 2 to the 4, which is 16, is strictly superior than 9. Okay, suppose 2 to the k minus 5 is strictly superior than k, where is k is strictly superior than 8. Okay, so I'm going to multiply both sides by number 2 here. I get here 2 is multiplied by 2 to the k minus 5, which equals 2 to the k minus 4, which equals 2 to the key plus number 1 minus 5. Okay, we strictly superior. Since we multiply both sides by number 2, I'm going to multiply this one by number 2 as well. So I get here 2k, which equals k plus k, which is strictly then k plus number 1. Okay, like this. Thus, for all n is strictly superior than 8, we have 2 to the n minus 5 is strictly superior than n. Okay. So previously we have proven this one by using the induction hypothesis. So we know this one is strictly superior than n. Okay. Now let's make the combination between this one and this one. Okay. So I'm going to replace n with ab. So I get here 2 is multiplied by n minus 5 is strictly superior than n, which equals a is multiplied by b. Okay, let's multiply both sides of this inequality by a. Okay, I get a here, I get a squared here. Then this one equals c plus number 1. Okay, then we know c equals b. Okay, so we get b plus number 1 is strictly superior than a squared b. Let's move over this b to the right. I get here 1 is strictly superior than a squared b minus b. Let's take b as a common factor. Let's take b as a multiplier. We get here 1 is strictly superior than b factor a squared minus number 1. Okay, here is a thing here. Since we are dealing with natural numbers, which means the minimum value a can take, which is number 1. Okay, if I'm going to replace a with number 1, it gets 0 here. But if b, we know b is a natural number as well, which means 1 is strictly superior than 0, which is okay. We don't have any contradiction here. Okay, but the problem, if a strictly superior than 1, you will have a problem. For example, let's take a equals 2. You get 4 here. 4 minus 1, which is 3. 3 is multiplied by another positive number, which means you have 1 is bigger than 3, which is impossible. So in order to create a contradiction here, we need to assume a equals 1. If a equals 1 doesn't work as well, if a equals 1 doesn't work here, which means you have a contradiction. Okay, let's suppose, by the way of contradiction, suppose a equals 1. Okay, let's replace a with number 1 everywhere. Okay, so let's take this one. We get c plus number 1 equals 2 to the n minus 5 is multiplied by 1, which is 1. Okay, I'm going to leave this one as it is. Let's replace this one with number 1 also. We know n equals a is multiplied by b, which equals b. Let's create this equation. Let's make this product, this one which we have here. So we know c is multiplied by c plus number 1. c will be replaced with 2 to the n minus 5 minus number 1 by taking number 1 to the right. Okay, we'll get here 2 to the n minus 5 minus number 1. c plus number 1, it will be replaced with 2 to the n minus 5. 2 to the n minus 5. Okay, we know this one equals to this one, which equals n is multiplied by 2 to the n minus 5. Okay, since n is strictly superior than 8, which we have here, we are allowed to divide both sides by 2 to the n minus 5. Okay, will be ended with this one equals to n. So we get 2 to the n minus 5 minus number 1 equals n, because this one is already cancelled out. This is for all n is superior equal to 9. Okay, or n is strictly superior than 8. Okay, which means the difference of these two terms equals 1, which means this one is bigger than this one, which means this one is bigger than this one by number 1 only. Okay, which means the difference of this equals, which means the difference of this one equals 1, which is impossible, because this one, as n is growing up, make this difference a huge difference. Okay, not only 1. So whatever the value of n, you have this difference is not equals to 1, which is different than 1, because the exponential form is growing up quickly than linear form. Okay, this is the difference. So we can do that. It's more simple to, we know n is super equal to 9, okay, or n is superior than 8. Let's subtract minus 5 from both sides. I get here n minus 5 is super equal to 4, okay, which equals 2 square. Let's raise number 2 as a power on both sides. I get here 2 to the n minus 5 is strictly superior than 2 to the 4, like this, okay. And I put minus n for both sides. I get here 2 to the n minus 5 minus n strictly superior than 2 to the 4 minus n, okay. We know this term equals number 1, okay, which means 1 is strictly superior than 2 to the 4 minus n, okay. Let's take this n to the left, plus n strictly superior than 2 to the 4, okay. We know, as we said before, n is strictly superior than, n is super equal to 9. Let's split this one into two terms. I get 8 plus number 1, and move over 8 to the left. I get n minus 8 is super equal to 1, okay. Let's add n on both sides. I get 2n here, okay. So which means this one is super equal, this one is smaller than 2n minus 8, okay. Let's move over minus 8 to the right. I get here 2n is strictly superior than 2 to the 4 plus 8, which equals 24. Divide both sides by number 2. I get n is strictly superior than 12, okay. But we have n is strictly superior than 8, okay, which is impossible. In the other word, the minimum value of n, it was 9. The minimum value of this one, 13, okay, which is impossible. So the true one is this one not true, which is a contradiction. What does mean a contradiction? Which means n cannot be strictly superior than 8. n belongs to this set. Since we have shown n equals 1 is not a perfect square, which means it's going to take the following values: n, 2, 3, 4, 5, 6, 7, 8, not above 8. Okay. You are going to set these solutions after you show when we have c is an even. We have shown before c plus number 1 is an even and c is an odd. Now we are going to do the inverse. If c plus number 1 is an odd and c is an even, you can do that case. It's similar to this job that I have done before, but it's less work than this one. This one has more work, okay. So it's more simple to do the same thing. So at the end you are going to, you will find it's impossible to have the solution above this number as well. So which means you will have this set as a solution. So then after replacing individual integers into this equation by replacing n with its value, you will find n equals 2 doesn't work, number 3 doesn't work, number 4 is okay. So you will find the solution of n equals 4 corresponds with x equals 6 as a perfect square, okay. Then this one doesn't work, this one is okay. So we found also another solution, which is n equals 6 corresponds with x equals 14. Then keep going up, you will find 7 is not a solution, 8 is not a solution, okay. So the only solution you are going to find just these two solutions. If you replace n with its value here, is given as a perfect square. I have ended this video. By the way, don't forget to hit the subscribe button and support the channel. And thank you for watching. I will see you next video. Bye.